So I first wanted to show you how we're going to be able to use Laplace transforms to solve differential equations that we may not otherwise know how to solve. But now I want to spend this video calculating some Laplace transforms. One, because we will ask you to do it, and two, it will demystify the table a little bit. We may not be able to, or we may not take the time to calculate everything in there, but we can certainly calculate, for example, L of 1, which we used in the last video. So we're going to use this definition of Laplace transform, and remember that was the integral from 0 to infinity, so improper integral. We have an e to the negative st, and then we multiply by the function. So here we're going to multiply by 1 dt. And all we need to do is calculate this integral. So remember, with an improper integral, we're going to take the limit as a goes to infinity, integral from 0 to a, e to the minus st dt. Not a difficult integral to evaluate. This is e to the minus st over negative s. This goes from 0 to a. We have an s in the denominator, so note here that s cannot be 0. We'll take care of that in a minute. And then this is the limit as a goes to infinity. We'll plug in the bounds, so this is e to the, plug in a for t, right? Leave s, so minus as over negative s. And then minus a negative sign is a positive, but that's the negative sign. E to the 0 is 1, so plus 1 over s. Okay, and now this depends on what sign s is, actually. So this is, if s is positive, and a is going to be a really big number, then e to the negative as is going to be really, really small. So this part will go to 0, and we'll get 1 over s. So 1 over s if s is positive. If s is negative, then, and a gets really big, then this whole exponent will be a huge positive number, and then there will be no limit. So this limit does not exist or diverges. There's another word for does not exist if s is less than 0. Now let's check s equals 0 separately. So we'll do that over here. If s equals 0, then what are we doing over here? We have the integral from 0 to infinity of e to the 0 times 1, so that's a total of 1 dt. And this is not an improper integral we can evaluate. This will diverge. You can either calculate it or think of it as the area under the curve of the function 1 from 0 to infinity. That's not going to be a finite number. So actually it diverges if s is less than or equal to 0. Okay, so this is what we saw in the table, right? The Laplace transform of 1 was 1 over s if s is greater than 0. Another one we can calculate is the Laplace transform of sine of b of t. Okay, same thing. We're going to go integral from 0 to infinity, e to the negative st, and then replace it with the function. So now sine of bt dt. And look, this is now our favorite integral to evaluate in this class. We're going to do an ugly integration by parts. There's constants in here. This is going to be fantastic. Okay, I'm going to do it as an indefinite integral first, so that we don't have to worry about bounds. Okay, so let's try to do this not too slowly. U is e to the st, v is going to be, well, dv is what's here, I guess, is going to be sine of bt dt. So that means v is the integral of that, so negative 1 over b cosine of bt, and then du is negative s e to the negative st dt. Okay, so the integration by parts says we take u times v, so negative 1 over b e to the minus st cosine of bt minus v du. There's a minus and a minus and a minus in the formula for integration by parts, so that a total of 1 minus. We'll write the constant in front, so s over b. We're integrating with respect to t, so s is a constant. Very difficult to keep track of. Then this is e to the minus st cosine of bt dt. Okay, that's one integration by parts. We need to do another one so we can collect the e's and the signs on one side. Okay, so we're going to do this again. Now it matters which one we choose for u and v. We need to choose the same one for u. So u is e to the st. Dv is cosine of bt dt. So v is going to be the integral of that, which is 1 over b sine of bt, and then du is going to be the derivative of this minus s e to the minus st dt. Okay, so we'll come down here. We'll leave this here, e to the minus st cosine of bt, minus s over b, we'll open a parenthesis, and then put the remainder of the integration by parts here. We need a uv, so 1 over b e to the minus st sine of bt, and then minus v du, right? So minus, there's a minus sign here, so now there's two minuses, so in total it's a plus, s over b integral of e to the minus st sine bt dt. Okay, we've done it. We're going to expand this, so minus 1 over b e to the minus st cosine of bt, expand that, so s over b squared e to the minus st sine of bt, and then minus s squared over b squared integral of e to the minus st sine of bt dt, and that was equal to integral of e to the sine t bt. So we'll collect that on the same side. We're going to have a 1 plus s squared over b squared. We'll actually find a common denominator. So 1 plus s squared over b squared is the same as, sorry, you can't see that, b squared plus s squared over b squared. The integral we're looking for, e to the minus st sine of bt dt. And we'll go ahead and introduce the bounds now. So instead of writing plus a constant, we'll just evaluate these with bounds. So this is minus 1 over b e to the minus st cosine of bt minus s over b squared e to the minus st sine of bt. And we're evaluating, we could take a limit, but we can also evaluate the limit as we go along. As long as we don't write down a step where we plugged in infinity, we're good. Okay, so what happens on this side? This is, let's see, as t goes to infinity, as long as s is greater than 0, then, so I'm just going to write, we're considering s greater than 0. If s is less than 0, obviously all of this is going to diverge. So only true for s greater than 0, then these will go to 0, and these won't get big enough to counteract it, so the whole thing will go to 0. So we have 0 minus, and these all have minus signs, so we'll actually write plus, and then these will be, think of these with positive signs. Sine of 0 is 0, so this term will go away. Cosine of 0 is 1, e to the 0 is 1, so it's going to be plus 1 over b, as long as s is greater than 0. And so then, so that's just 1 over b, so we can solve for the integral that we're looking for finally. We're going to multiply both sides by b squared over b squared plus s squared. The b squared will, one of the b's in the b squared will cancel out with this b, so we'll be left with b over b squared plus s squared. And that's the Laplace transform of sine of bt, which we solved for in the video, or in the table. This is the answer that we saw in the table.